In this video, we're going to talk about two things. The first thing we're going to address is something known as conditional statements, and then the second part, we're talking about dilations. So the first thing is conditional statements. So these are those statements when they are written in an if-then. Okay, so this is important. So all conjectures and theorems are often written in an if-then statement. So it forms that conditional statement. So think of your if as kind of your hypothesis, right? And then the then is your conclusion, right? So it's a statement. And these statements really can be set up where they could be true or false, right? So it doesn't have to necessarily be true, right? We're going to talk about kind of if it has a counter example, right? So here are just some conditional statements examples. Two of them are highlighted because those have to do with our geometry section, right? So if my cat is hungry, then she will rub my leg. Is that true? I'm not sure. I don't have a cat. But there might be other reasons why she rubs my leg. Maybe she wants attention. Maybe she wants to scratch. Maybe she has to go to the bathroom. I don't know. But if we look at our first highlighted one, if a polygon has exactly 4 sides, then it is a quadrilateral. This is a true statement. I'll put a little T next to that. And that's true because all 4 sides, anything that has 4 sides is always called a quadrilateral. Hypothesis, conclusion is quadrilateral. The second one, right? If triangles are congruent, then they have equal corresponding angles. That is also true because if you recall triangles, so let's just pretend that these triangles are congruent. I'm just putting little tick marks here based on side, side, side. Then that means the corresponding angles also have to be congruent. So that angle would match up with that. This angle would match up with that angle, right? And then finally this angle right here would match up with that angle. Okay, so again, it's an if-then statement. Now, what happens if I kind of switch those around, right? So if we kind of reverse our thinking, okay, we can come up with known as a converse, right? So a converse is the reverse order, right? That's what a converse is. Converse of the statement is the reverse order of your statement, okay? So if we know so if we understand what a converse is as the reverse order, let's go back to our previous two problems. And I want to come up with the converse for my first one. So I'll call this number 1. So I'm going to say converse for number 1. Okay. So if a polygon has exactly 4 sides, then it is a quadrilateral. All right. So converse would be if a polygon is a quadrilateral, then it has exactly 4 sides. And you should always ask yourself when you write an if-then statement, is that true? And if it's not true, we want to come up with what's known as a counterexample. So if a polygon is a quadrilateral, then it has exactly 4 sides. That is true, right? All quadrilaterals have 4 sides. All right, so the second one, so we'll call this number 2. So our converse for number 2, converse for number 2. So again, if triangles are congruent, then they have equal corresponding angles. Sorry. So we can say if angles have equal corresponding angles, then conclusion, they are congruent. I'm going to abbreviate to congruent. Now, is that one true? And that answer is false. That is not true. Because if you recall, right, the only way to test out if triangles are congruent, right, is through side, 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 congruency, side, angle, angle, side, angle, 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 side, and hypotenuse, leg. So we don't see just having angles. We don't see A as a theorem. So because we don't see A, it is false. So my reasoning that I gave you is what is known as a counterexample. So a counterexample is a statement showing at least one situation where a statement is false. Okay, so again, this is just if we see an if-then statement, always ask yourself if it's true or not, and can you come up with a counterexample of why something is not true? And that's all conditional statements are. So the next thing that we want to talk about, we're going to switch gears now, is talk about dilations. Okay, and that actually will kind of lead us back to our last converse. If angles have corresponding measurements, right? Are they really congruent? We're actually going to see that they're not congruent, and they actually are similar to each other. There's something known as dilations. So that's what we're going to talk about right now. So dilations, really all you need to remember is this. It enlarges or reduces, right, a figure while maintaining its shape. So it doesn't change its shape. Okay, so let's take a look at some dilations. What would dilations look like? So you see this lovely handout. And so things that I want to think about while we go through this is what does the original picture and the new dilated picture have in common? If you have any wax paper at home, look to see what's happening with your angles. And do you notice anything about the side lengths of things? Okay, so the first thing is this is a quadrilateral, so I'm just going to call it A, B, C, D. And this is, again, the original picture, so we're just going to say original. And our original does have a dilation of 1. So that means that nothing changed. Okay. So what I want to do is I want to make a new picture, and I'm going to call it A prime, B prime, C prime, D prime, and this will have a dilation of 2. Okay. I'm going to say that my point of dilation, so I always have to start somewhere, is at 0, 0. It's at this point. So everything's going to start here. Okay, so ask yourself, how do you go from your dilation to one of these points? So if I go from my point of dilation to A, that means I'm going to go up 2, I'm going to go over 3, so that gets me here. And then I'm going to go up 2, 1, 2, and then again over 3, and I will get to my A prime. How can I get to D? I'm going to go down 2, and then over 1. So that means I'm going to go down 2 and over 1 more time. I'll get to D prime. I can go down to over 2, right? And that means I can go down to over 2, and I get to C prime. How do I get to B? I'm going to go up 2 over 1. So up 2 over 1, and now I'm going to get to B prime. So if I connect these points together to the best of my ability, it makes a new graph, new shape, and stuff like that. So take a moment, you might want to pause the video, think about it. Again, what do you notice about the new picture and the original picture? What do they have in common? What do you notice about the angles? Do you notice anything about the side lengths? Okay. All right, so what should we have noticed? Well, I notice that AB is parallel to A prime, B prime. They both have a slope of 0. So does CD and C prime, D prime. I noticed that. I also noticed that B prime to C prime is parallel to B to C. I also noticed that A prime D prime was parallel to AD. Right, so it didn't cross. That makes sense. We were kind of following the same measurements. What else did I notice? Well, if I took wax paper, I should have noticed that this angle was congruent to that angle. So my angle A was congruent to my angle A prime, and same thing for all of the rest of them. They were all congruent to each other. They didn't change. Okay. And again, I can't show that on the video, but if you had wax paper and graph this out, you can really see that that angle really does match up with that angle. What else do we notice? Well, I noticed that for the A's AB length was 4. And then I noticed that A prime, B prime, right, ended up being 8, right? I can also see that CD was 3 and C prime to D prime ended up being 6. So it almost looked like it doubled, all right? So your shape, so the shape doubled in size. And that kind of makes sense because you had a dilation of 2, okay? Now, we would have seen that for BC, except we didn't necessarily have to do our, what's it called? Pythagorean theorem to find the missing side lengths. But all side lengths are going to double. All right, let's do one more. And let's see if this actually holds up. So I'm going to make some predictions for A prime, A double prime, B double prime, C double prime, if I do a dilation of 3. So these are my predictions. So I predict all sides, again, will be parallel, right? I predict that my it's going to triple in size. And I also predict that angle A and all the angles, right, will be congruent to my new angles, right? So that's what I predict, okay? So, so let's go ahead and see if we're actually correct. So again, up 2 over 3, up 2 over 3. So I'm going to go up 2 more and then over 3, A double prime, down 2 over 1, down 2 over 1, down 2 over 1, D double prime, and then down 2 over 2, down 2 over 2, down 2 over 2, and then up 2 over 1, up 2 over 1, up 2 over 1, B double prime. So from 3 all the way to 9, right? That is the length of 12. So I know that A double prime, B double prime became 12, and 4 times 3 does give me 12. Here, -6 all the way to 3. So C double prime, D double prime is 9, and that makes sense. 3 times 9, 3 times 3 gives me 9. So my sides did triple. If I had my graph paper, or my wax paper, I should say, I should notice that my angle A did not change from my A prime to my A double prime. So that also is true. And all of my angles actually ended up being the same. Right? So again, kind of important things to be thinking about. Okay. So in our notes, things to remember is that if we have a dilation that is greater than the number 1, right? That means that our graph is going to become enlarged. It's going to get larger. Now, if everything larger than 1, right, 2, 3, 4, 5 gets bigger, that means if your dilation is between 0 and 1, it's going to reduce, right? So we just didn't see the reduction. And again, what happens if our dilation is equal to 1? It's going to stay the same, stay the course, okay? We know all of our sides, so our shape, again, shape maintains the same thing. It just looks a little bit different. So if you kind of want to test this out and see if this is true one more time, by all means, try doing it for this one by a factor of 3. So again, you'll notice that your F and your H and your G are all going to be the same. Okay, but again, notice that our point of dilation did change just a bit. Okay. All right. So if you tried this out and try to do a dilation of 3, again, you'd start at the dilation and you would, let's do F first. So I'd have to go up 2 over 2. So I'm just going to follow that pattern, up 2 over 2, and then up 2 over 2. So here is my F prime. I'm at 4, I have to go to 14, which means I'm going to go to 24, which means I'm going to go to 34. G double prime, or sorry, G prime, not double prime. Should be all the way over there. Boop, boop. All right, and then I'm going to erase this part. Oops, didn't mean to erase all of this. So up 2 over 2, up 2 over 2. Yeah, okay. So I want to make sure I got the same spot. Boop, boop, boop. All right, so how do I get to H, right? I got to go up, it looks like 3. So 1, 2, 3. And then I'm going to go over 1, 2, 3, 4, 5, 6, 7, 8, 9. So up 3, 1, 2, 3, and then over 9, 2, 4, 6, 8, 9, and then 1, 2, 3, 2, 4, 6, 8, 9. Right? And then that is my H prime. So if we connect our points together, bam, bam, a bam, bam, and then last but not least, those values. Okay, not the best second triangle. I apologize for that. But we can see that that our angles should be the same. So this is going to match up perfectly with this. This guy is going to match up perfectly with this. If we wanted to find the side lengths, again, use Pythagorean theorem. Okay, so all of these graphs are what's known as similar, right? So the big thing to remember is that similar polygons, right? So any shape can be mapped onto each other with a sequence of rigid transformations and a dilation. So that means it's going to get larger and smaller. And most importantly, our symbol for similarity is now just the squiggle sign, right? So if we remember, this is our symbol for congruency. So all together, this is congruent, right? We're going to take away, because equal, that's what it's saying. They're equal to each other. So all we're doing is we're taking away the equal sign, and we're just making it similar. So they have stuff in common to each other. Now, are all of our polygons going to always be on graphs that we can figure out our angles and things like that? What happens, side lengths, double, and whatnot? Okay, and the answer is no. So we have to be able to look at figures off of graphs and kind of think of some strategies, right, to figure out how much they're being dilated by. So dilation, right, is the term that we use for when we're talking about making a polygon larger or smaller. Okay, we can also use the word scale factor. Okay, so scale factor is very similar, right, to dilation. So if I see a scale factor of 2, I know I'm doubling. Scale factor of a half, I know that it's going down. Okay, so if we take a look at, say, these 2 letters, right? So C, here's the original one, and then this is the new. So if we compare our heights, right? So anytime we compare our heights, we're always putting our new over our old, right? So notice that 24 over 8, this is going to reduce down to 3. And then notice that 8 over 6 also reduces down to 3. So notice that your ratios are equal. All right, so if I wanted to go from my original to my new, it looks like this is tripled. This triples my side. So this is how we find our scale factor, or AKA our dilation, how much things are going by. We take our new figure height divided by our old figure height. Okay, but that's not the only way that we can kind of verify the proportions are correct, right? We could look at 8 over 6. So let's just take our old, right, or our original, right, and notice that 24 and then over 18. So again, 24 and 8 go together, 6 and 18 go together. So the number 2 goes into both 8 and 6. So this will give you 4 over 3. Oh, sorry. Yeah, oh yeah, sorry. 2 goes, yeah, 4 over 3. And then 6 goes into 24 and 18. For a second, I thought I wrote 3 over 4. So 24 and 18, 6 goes into both of them, and notice that you get 4 over 3. Notice again, your ratios are equal. The problem with this is that it doesn't say, this doesn't give us our scale factor. So it doesn't give scale factor. Okay. So one does when we approach it as a new over the old, but if we're just comparing our sides with our new sides, it's not going to tell us our factors. But again, the most important part is that they are equal. Okay, now how can I use that information to potentially solve something, right? So what happens if I knew that this side length was 9, right? And I wanted to find this side length. Well, what I could do right, is I could know that my scale factor is 3. So there's two ways. So two ways to do this. So I could first find my scale factor. So I found my scale factor already, which was 3. And so I know that I'm going to take my 3, I'm going to multiply it by my original side. I'll make that equal to 9, which is what I want, right? And then I can solve for x. I can get x is equal to 3. That's one way. The second way is you can set up a proportion. So set up a proportion, right? So I know that, and it doesn't matter which goes on which. So I can go 8 over 24, perfectly fine. But if I start with my original one, that means that x is going to go over 9. I can go ahead and I can multiply. I always like to simplify first. So I'm going to simplify my 8 and 24 when I can. So 1 over 3, x over 9. I can cross multiply and notice that I still get 9 is equal to 3x, right? And this brings me back, right? As long as your proportions are equal to each other, it should not matter how we set up our equations.